Well, welcome back, everyone. Happy last day of class. Um, Today, I want to talk a bit about time series analyses and give you a chance to play around with the demo notebook on network dynamics in fMRI data during story listening. Before we get into that, though, would anyone like to bring up any topics for discussion about any of the materials so far, or assignment 5, or any other computer science or programming related questions that you were hoping we'd get to this term? I want to give you a chance to do that.
Do you have any like 5 quick tips? It doesn't have to be 5, just like a few quick tips on how to like write good code if I was going to put it on like OSF or something like that.
Yeah, actually, so as part of the Mind Summer School, which I encourage you all to participate in when the world opens up again and we restart that. I do like a little tutorial on good coding practices, which is kind of aimed at, it's aimed at both like writing shareable code that you'd put on OSF or GitHub, public GitHub repository or something like that, and then also at like what are some practical tools for kind of doing hackathon type projects that you are working with other people on. So they're you want to do quick code development, but also in a shareable way. So I'm happy to send. I kind of have 2 versions of that talk. I think one's like longer and more in depth, and then the other is kind of shorter, but probably fine for for a quick overview. So I'm happy I can share both of those on GitHub, but I have YouTube links.
That'd be awesome.
Yeah, sure. And then like as a longer term thing, in general, the Mind Summer School is one way to kind of get into this stuff more and develop some good habits there. Anyone else?
So I had a question about the assignment.
Sure.
The Magellan. So I think I'm fine with all the sort of the first part, but the Magellan, as I understand it, as the participants moving around, they basically have like a radius or something around them. And any landmarks that are within that radius, their memory is 1. It's sort of the max value. As soon as one of those landmarks leaves the radius, it begins decaying until it decays to its minimum value.
That's right.
And then as soon as the radius overlaps again with that landmark, the landmark is now within the radius again, then it gets set back to 1. And then that's just all the algorithm's doing. Is that correct?
That's right. Yeah, that's right.
Okay.
Yeah, so it's actually like a simplified, the like real model is a little bit more complicated. So it involves like building a 3D reconstruction of so if you wanted to like solve this for real, you'd have to like build a 3D reconstruction of the environment and then take into account like your field of view and what you can actually see. But there's like a lot of bookkeeping there, and it's not all super interesting. So this is like a kind of noisy approximation to that. But the idea is like stuff you can see, which obviously you can't see behind you, but for this assignment you can. And it's a reasonable approximation. It's not super terrible. So it's like you can think of it like stuff you can see now you have perfect memory for, and stuff that is right behind you. So like you've just seen it, you can also have perfect memory for in this assignment.
Thank you.
Sure. Any other questions, comments, ideas, thoughts? All right. Okay. So let's dive into the Module 9 content then on time series analysis. So I thought I could, well, actually, maybe I'll do a poll first. Who has worked with time series data before? And or like, okay, no one. Yes, you've probably, okay, now getting a lot of 50% maybe, great. Okay. Okay, so I'll give like a quick intro maybe then. As the name implies, time series analysis is all about analyzing data with a temporal component. So in other words, like data where the observations are ordered in time, and often like time is a key feature of interest that you want to understand. So in like neuroscience and psychology research, most kinds of data that we work with end up having some sort of time component. So probably the most common time series data we work with are brain data, where you like get measurements from the brain at regularly sampled intervals, or behavioral data, where you like have your participant doing something or you measure something about what they're doing, like often also at regularly sampled intervals. It's often convenient to organize your time series data into a data frame, like a pandas data frame, where the index or like the rows of your data frame correspond to time points, and then the columns correspond to features. So if you're dealing with brain data, like features might be EEG channels or fMRI voxels or regions of interest, et cetera. And then the values in your data frame might be like voltages or spectral powers or bold activations, perhaps normalized in some way, et cetera. And then if you're dealing with behavioral data, then features can be anything really, but to give you some examples, you might want to have features for like different stimuli or stimulus characteristics that participants encounter or like produce from memory. Or like ratings or other like, numeric sorts of behaviors that people can produce, or words or linguistic data that people produce or encounter or, say to each other, or the underlying text embedding vectors of those words. You could have visual stimuli, like where your features are like different pixel values, audio or speech data. Again, that could be like waveforms or some sort of processed version of that type of data. Button presses could be keyboard buttons or like a button box sort of response, et cetera. So that's like the sorts of that's kind of an overview of the sorts of data we often talk about when we're talking about time series data in like neuroscience and psychology. Then when you go to analyze time series data, oh, did anyone have a question? No, okay. When you go to analyze time series data, you can essentially ask the same sorts of questions that you'd have wanted to ask with non-time series data. So for example, you might want to know like if someone's brain responds differently during condition 1 versus condition 2, and stuff like that. So that's one thing you can do with time series data. But then there are also a bunch of additional questions that you can start to ask if you know when different measurements were collected or behaviors were collected. So for example, you could start to look at order effects, like if A comes before B versus after B, are the responses to A meaningfully different? Or like in general, are people sensitive to order effects? And at what time scales, like how far back in time do you need to go in order to account for or explain some moment or stimulus presented at that moment, to explain like how it affects someone's brain activity patterns or future behaviors. So that could be interesting. You can also start to look at temporal patterns, which can look different from static patterns. So just like movies can like carry or convey information that's different from static images, considering the time dimension of your data can like yield new insights or provide some nuance into interpretations of your data. There are like a few kind of standard approaches to like, know about. So one approach is to look for periodicities in the data. So for example, by looking at like sinusoidal components of the data. So for example, like, is there some recurring pattern, and what are the timescales of those recurrences? And then from a practical standpoint, the MNE library has a lot of useful functions for decomposing time series data into its constituent frequencies. So that's probably the best library to use for those sorts of analyses. You can also start to build predictive models. So for example, maybe you want to ask like how well you can predict what someone's brain is going to do next, and then like see how good your predictions are under different circumstances. So if you're familiar with like the event boundary or situation model literatures, you might have heard about the idea that like when we're in a particular situation or experiencing some event, our brain kind of enters like a stable state. And then when our current situation changes, or like in other words, when we cross an event boundary, our brain quickly transitions into a new stable state. So within a single situation, we can often accurately predict what someone's brain is going to do in the next moment. But then like predictive accuracy is going to fall off dramatically across an event boundary. So that can be interesting to look at. In practice, the SK time library has some useful implementations of temporal predictive models. So that's like a good place to start for that sort of thing. There are actually like a ton of time series prediction models out there because they're so useful for such a wide like range of applications. But SK time has like the most popular kind of implementations of, or the implementations of the most popular models. And then another like really neat library is the Facebook profit model. It's like a newer library that Facebook put out, and it's got some cool stuff in it. So it can like take into account like seasonality and like time of day effects and all kinds of neat stuff. It's kind of like the cutting, like an amalgam of the cutting edge of time series prediction. Okay. And then kind of a third type of model that we'll spend a nice chunk of time on today, or digging into today, is concerned with interactions between different features. So for example, like if you have some set of brain structures that you've recorded, like maybe you want to know like how are the structures interacting or like transmitting information back and forth, or from other, sending or receiving from other structures, maybe as a function of what someone's doing. And so if you want to look at those sorts of patterns in your data, then two libraries that are useful that you'll get some practice with today are the Brainiac and TimeCore libraries. So they're really about, or pieces of those libraries are aimed at looking at like network dynamics. And then in the example notebook, you'll look at network dynamics in brain data specifically. Okay. So any questions? I know that's like a kind of pretty high level overview, and this is a super deep field, so that's not really a sufficient overview of time series analysis, but maybe it gives you a sense of kind of what the game is here. Any questions on that so far? Okay. Yeah, so what I thought we could do for at least most of the rest of our time today is like give you a chance to dig through the demo notebook I put together. So the notebook walks you through one approach to looking at network dynamics in fMRI data. And I thought we could, like we've been doing, break off into smaller groups and go through the notebook to make sure you understand it. And then we can either stop there or discuss some interesting things to try out next, depending on timing. Okay, So with that,
Jeremy,
Oh,
before we go into
yes.
it seems like at least two of us have run into a problem with the Docker container. That
Okay.
that something does not seem up to date in the Docker container that the notebook requires. What was it called? Lisita, can you take over?
Oh, sure.
My head.
Do you want to share your screen and we'll?
Oh, sure. I mean, I'm trying and stuff, and I might not be able to produce the error this very moment. But in the first cell of the HTFA notebook, you import statements or importing like Nylearn, NL tool, etc. The error that I saw was at the import NL tools line. It was like no, some sklearn module was not found. Yeah, I know. And like, it at least seems like in the Docker image that the NL tools version specified is the latest one. So I didn't think it would necessarily be NL tools. So then NL tools also is like calling Nylearn, which is actually calling sklearn. So then I'm trying to kind of like at this very moment, trying to like experiment with like, well, what try to install Nylearn in the cell before. But I'm also having this issue where like the notebook keeps just dying and restarting before I can actually do much with it. So that's kind of where I'm at right now. So I don't know if that's really informative, but
did anyone get it to work? You got it to work. Okay, Sarah got it to work.
Amazing.
And did you? Okay. Interesting. Well, one option is instead of breaking off into groups, I could just screen share and just like kind of walk you through things. I'm glad at least one person got to work. That is nice. Okay. Okay. Well, why don't we do that? And then I'd love for you to be able to actually apply this stuff to your own data. So, well, if anyone would like to get the Docker image up and running, maybe just maybe like post on Gitter or reach out to me or Paxton, and we'll, help you out. It's obviously not going to be required to get it working for this class since today's the last day. But if you want to do that, I'm happy to help out, and I'm sure Paxton would be happy to help out too. I'll volunteer him for that since he's not here. Okay. Okay, so let me share my screen. Hopefully this is the right one. Okay. Can you all see that? Okay. Okay, so let's see. So there are kind of two pieces to this notebook. The first piece is using an approach, it's called hierarchical topographic factor analysis. What that means, well, it doesn't so much matter what it means. Essentially what comes out of that model is you feed in an fMRI data set, and what you get out is a picture that looks like this, of like where so if you think of the brain as a network of interacting components, a useful thing to do if you want to summarize what's happening is to figure out where the nodes of that network might be located in the brain. And so you can think of this model as like you feed in a data set and out comes the locations of these nodes, which are where these dots are. And then a neat feature of the model is that if you have data from many people, these nodes aren't necessarily going to be located in the same locations across people. And so it tries to find like an equivalent network in different people where the nodes are located in like almost the same locations across people, but not necessarily the exact same locations across people. And then you can start to like look at analogous network patterns across different people's brains, even if their like voxel labels don't match up exactly. So that's the idea of this HTFA model. So we can walk through how that works. And then the second piece is once you have this network, you can do interesting things with it. So also another thing that comes out of this HTFA model is a time series of like what each node is doing at each moment. So like its activity pattern, you can think of it like. And then you can feed that. So you get like what each node is doing in each person at each moment. And then you can feed that into this network dynamics model that takes a time series of like activity patterns or measurements or whatever, and outputs a like pattern of network dynamics at each moment. And so you can think of it like if you have all your nodes arranged on like the kind of outer ring of this circle, one way to visualize it is to say like, okay, here's what the network looks like at one time point. And then as you like change, go forward in time, you have different nodes interacting at different moments. And like maybe, there's some interesting changes that correspond to things that are happening in the story that people are listening to as these patterns are recorded. So that's one way of looking at these. And this is called a chord diagram. So that's kind of a neat way to visualize the data. And then you could say like, okay, here's what this chord diagram looks like if you're listening to a story. And then here's what it looks like if you're just like lying in the scanner with your eyes open. And so there are some differences there. And we could start to quantify them.
Jeremy, is there any way we can see where its nodes are on the brain map?
In the brain, yeah. So that's the next type of figure here. So here is a different way of visualizing the data. So here, like these different dots are each black dot here is a node. And then the red lines correspond to like connections between nodes at that moment that are reliably positive, and then blue means like reliably negative. So like, in terms of like the sign of the connection. So like when one region activates, is the other region's activity going up and down in the same direction? Or then you get a red dot. If the other region is going up and down in the opposite direction, you get a blue line, sorry, a red line, not a red dot. And then if there's no like correspondence between those regions that's reliable across people, you don't get any connection for that moment. And then these patterns change over time. So then if you look at the kind of top movie here, you have network dynamics as people are listening to a story. And then the bottom movie is like network dynamics as people are at rest in the scanner, or lying in the scanner with their eyes open, not doing a specific task that is sometimes called rest. And you can, visually you can see these patterns are different, but then the thing to do next would be to do some kind of potentially interesting analysis to start to ask questions, okay, like what are the specific differences moment by moment? And, are different, are interesting brain areas involved, etc.
So I saw this movie and then thought, is there any way we can see like what's the number of each node, which we can see on the upper visual that we just saw right before this movie?
You want to like click on different things. Yeah, you can't do that I didn't code that in. That would be
Gotcha.
That would be clever.
Because if that's
Yeah.
possible, we could kind of apply what we know about, theoretically, what we know about which part of the brain is supposed to connect together and etc. So yeah.
Well, so you do know so global centers here tells you the locations in 3D coordinates, or like M and I coordinates of each node. And those are ordered like in the same order that they are in this plot.
Okay, so we can just cross-reference if we want to know which part is no reference.
Yeah, so let me walk you through like what, maybe I'll walk you, that's kind of the high level, but maybe we could dig into the code a little bit, and then that might be helpful in terms of like giving you ideas for other things that one could do from there. Does that sound good?
Sounds great.
Okay. Okay. So let's see. So the first step of this analysis is like loading in the data. The data set is stored in this, well, I think it's kind of an interesting format. We can take a look at it. So it's got for each, oh, actually, so so here we have 27 participants. And so we have a list of dictionaries for each, one dictionary per participant. And if you look at any one participant's data, it's got these two keys in it, Y and R. Y is a matrix with number of time points rows and number of voxels columns. So this is like your fMRI data. So there are 300 time points and then 88,344 columns or voxels. And then R is a matrix that gives you the M&I coordinates, which is like where the 3D coordinates in the brain, if you haven't worked with fMRI data, of each of those 88,344 voxels. Okay. Does that data set type, or does that format make sense? So it's kind of like a convenient way of working with data, with fMRI data, because like it separates out the location component from the which is useful for plotting things on the brain, from the what's the time series data that I'm going to feed into some algorithm component. Okay. The next step is to wrangle this data set. So you can think of this as like the raw data. And the next step is we want to wrangle this data set into a new format that's compatible with the Brainiac library. And essentially, the Brainiac library likes data to be inputted in this same CMU format, except instead of time going down the rows, it goes across the columns. And so you just have to take the transpose of the Y matrix for each subject's data. So what this does, what this line does here is now HTFA data is a list, again, of length 27. So, and then if we look at, and then it also calls Y to distinguish it from its transpose. Now the data is called Z. So now Z for each subject's data has number of voxels rows and then number of time points columns, but is otherwise the same. And then the R matrix is exactly the same as the other one. So it has number of voxels rows and 3 columns, X, Y, and Z dimensions. There's some fancy setup needed for the Brainiac library which is what this code is doing. The Brainiac library is it's like optimized to work on a cluster with this particular method of sending information. A cluster is like a collection of computers where each compute node does some computation, and then the nodes kind of transmit information back and forth. And the library that enables that to happen is called MPI, which is, it's like stands for message passing interface. It's one way of like efficiently transmitting information across nodes in a compute cluster. And this code here, like basically sets up your Docker instance as a pretend cluster, and it's like pretending that you're, so it pretends that your local machine is a little mini cluster with however many processors are in your Docker container nodes, and which could be just one. And so a cluster of one node is not particularly interesting, but it would crash if this code wasn't there, because it would not be a cluster. Okay. And then, okay.
Jeremy, if you don't mind, it might be a dumb question, but how did you define node and cluster in this analysis? Like how many voxels included, or?
Yes. So yeah. So let me unpack that. That comes from this opts function. So opts is defined in a separate separate script, but we can look at this. And then it has this one flag, debug, which is either true or false. So here, okay, so I have debug mode is false. And so what it does is it returns a dictionary with like various parameters that are going to be passed into this model. So the number of nodes in the network is K. So here there are going to be 50 nodes. And then max global iter and max local iter refer to like how many times the optimization procedure runs. So what happened, the way this model works is you have some, like you basically start by guessing randomly where these nodes are, and then you average the answer, and there's like, the model's somewhat complicated and the details are mostly not important here, but there's like a model that describes where these nodes are located in general across people. And then each subject has their own model that's kind of a perturbation of that global model. And what happens when you're fitting the model is you start by guessing everything randomly, and then you pool all the guesses across people to get an estimate of where these nodes are located in the global model. And then you do some updating to make that guess a little better. And then you use the global model to initialize your new guesses about where each subject's individual model is going to be, where the nodes are for the individual subject. And then you run like 5 updates for the individual subject. Then you pool them and update the global model again. And then you go back and forth that whole process max global iter time. So in this case, 10 times. And then you just stop with whatever answer you got then. And then there are some other parameters that are related to like how you subsample the data. So it turns out this model, running it in its like unoptimized form, like would never finish before the heat death of the universe. And so since we don't want to wait that long, there are some optimizations that happen, and it uses a machine learning trick called stochastic inference, which is again beyond the scope of this course, but essentially you're not looking at the full data set at any given moment, you're just looking at a tiny piece of it, and that enables this to run quickly and not give you a terrible answer. and then verbose is just a flag that says whether it prints out stuff or not as it's going. Okay, so this params dictionary is where the number of nodes gets specified. Okay, and then n voxels and n time points is just like reading in from the data. So it's like the Z field of the first subject's dictionary. We're going to treat that as the number of voxels, the first dimension of that. And then the number of time points is however many time points that first subject had. And so we'll just pretend all the subjects have the same number of voxels and time points for this demo. Okay, does that make sense? Okay, and then the HTFA in capitals is a function from the Brainiac toolbox. And once you've defined your parameter structure, this is how you call it. So it's a little bit of a like cumbersome syntax, but that's how it's used. And I tried to kind of comment what the different lines are doing, but in general, yeah, I don't know. Let's see. So I guess I can walk you through it. So K is the number of nodes in your network that the model is going to find. Number of subjects is how many subjects you have. Max global iter and max local iter are those like optimization parameters, and then max voxel or voxel ratio and TR ratio are like other, or in max voxel and max TR. Those are all related to the stochastic inference piece, like how much of the data do you look at for any given update. And then verbose is like, do you print out like progress statements along the way? Most of these have default values if you don't specify them, but okay. And then that chunks along once you run it and gives you an answer. And then, oh, actually, no. What happens first is it just gives you a model object that is not fit to anything. So this actually gets returned immediately. And then what happens is it checks to see if the answer has already been saved. If so, it loads it in. Otherwise, it fits the model, which takes a really long time. I guess it takes like 20-ish minutes in debug mode, and then in not debug mode, it takes like a day. So if you just run it on your laptop, so it's pretty slow. And then it saves the answers. Pickle is this package that saves and loads arbitrary Python objects. And so it's really useful for like storing a variable that you might want to get back later when you like pick up again. And so that's what I'm using here. And then, oh, this is kind of a useful trick. So a useful way to make sure that like your saved out model is going to be loaded incorrectly is that the first time you run your code, instead of using the result from your like fitted model directly, you can save your first fit to disk using this pickle function, pickle.dump. And then you never look at the original thing. You just always use, even from that very first time, you use that loaded in pickle. So that way it like prevents you from running into a situation where like your code only works if you use the output from the model directly, but there's some weird error you're introducing when you load in the kind of new data structure. Okay. And then HTFA to dict and dict to HTFA are helper functions that turn like a HTFA model object from Brainiac into a Python dictionary, and they can convert back and forth depending on so the thing that comes after the two is what you end up with at the end. So an HDFA to dict converts an HDFA object to a dictionary object. Dict to HDFA turns a dictionary object into a HDFA object. Okay. So this is like how you get the nodes of your network. Any questions there? Okay. Okay, once you have that fitted model, this next cell reads out kind of information from that model, and then that's like what we're going to use to like start doing network analyses. So we can read out like, okay, how many time points are there? Actually, that's just from the original data. And then this plot nodes function takes in a fitted HDFA model, a number of time points that I don't actually know why it takes in the number of time points because it's just static, but oh, it must, you know what? It must be, there's some kind of reshaping that happens to where you have to know the number of time points in order to figure out the number of nodes or something like that. Okay, and then a color map, it tells you like how to generate the set of colors that are going to be used to draw these things. And then global scale is like, what's the dot size for the global coordinates of the network nodes, and then local scale draws small, like potentially smaller dots or differently sized dots for each individual subject. So the big network is going to be drawn in dots of size 100, and then the individual subjects are going to be drawn in different colors of size 25. And then you get one dot per node, and here everything is pretty much overlapping, so there's very little difference across subjects. In the debugged version, where things don't run for quite as long, there's a little less agreement across people. So you can actually like see some variability. Okay. Everyone with me so far? Okay. Lots of thumbs up, that's good. Okay. This local params function now reads out from a HTFA model, like a fitted model, once you know the number of time points, it reads out like some useful variables from the model. And we can take a look at those. Let's see. Okay. Okay, yeah, so what this is returning, oh, okay, local params. So it's returning the subject specific parameters for each like individual person's network. The key things are, we might want to know like where the nodes are located, and that's what the centers variable stores. And so there are 27 subjects, so each one gets one set of centers. And then if we look at one subject, since we have 50 nodes in our network, we have 50 nodes that are located throughout the brain, and then they each have a 3D coordinate. So we have a 50 by 3 matrix telling us where those centers are. You can think of each center as like a spherical hub somewhere in the brain, or a spherical node somewhere in the brain. And so the radii of those nodes are given by the widths. And then weights gives you a number of time points by number of nodes time series that tells you like how each node is active in each time point. And then you get one of those for each subject. Okay. Does that make sense? Okay. All right. Okay. So another piece to this data set is some of the subjects. Oh, interesting. Sorry, I think I described earlier one of the network dynamic patterns was related to rest. It's actually not rest. So the conditions are you listen to the intact story, or people who listen to a scrambled version of the story where you got the same words but in a random order. There was another condition to this experiment where there are various other conditions in this experiment, but I guess I'm only looking at intact and the word scrambled condition here. So sorry about that. Okay. Okay, so for each participant, we have a file name, and you can see like intact or word in part of the file name. And that's going to be, we're going to use that to tell us which condition each of these 27 subjects ran in. This line, or sorry, these lines here are list comprehensions, which we've used before here. So the tricks here are like for each entry of this weights list, we're going to use enumerate to cycle through each weights matrix W, and then the index of the weights matrix is going to be I. And if the string intact is in that corresponding file name, then we include W in the list of intact weights, and otherwise we just ignore that set of weights. And then the scrambled weights does a similar operation, but here we're looking for the word instead of the word intact. So what we end up with is intact weights is going to be like, okay, so 18 participants, and then scrambled weights is going to be the remaining 9 participants, and then 18 plus 9 is 27, so that's a good sanity check. So every subject fell into one of those conditions. Okay. Finally, the time core, so intact weights is a list of length 18. And then if we look at one entry in that, that list, it's a matrix of size, number of time points by number of nodes in the network. And then every subject the data is of the same size. Next, we feed in the data set to the time core library. And again, somewhat of a cumbersome syntax, but what comes out is it's called dynamic intersubject functional connectivity matrices. And what we get is for each time point, a connectivity matrix. And where that 1275 comes from is actually, so a different way to view this is, so you can think of it as like a 50 by 50 matrix, connectivity matrix at each time point. So this is like the nodes that are sending information, the nodes that are receiving information, and then time point. So if you wanted to look at one connectivity matrix, you could plot it like this. and that would give you like 1 time points connectivity matrix. And then you get one of these for each time point. Okay. Where that 1275 comes in is it's, so because these, the way that I've computed connectivity here is using correlations, and which is a symmetric operation. And so you can efficiently store these matrices. So 50 times 50 is 2,500. But then if you let's see. So if you subtract 50 to get rid of the diagonal and then divide by 2, that gives you like just the upper or lower triangle. And then you actually have to add back in 50 because the diagonal in this case is actually informative, because it's looking at like similarities across people. And if you're looking at one subject's data, the correlations between a time series in itself is always 1. But here it's actually looking at a correlation between like one subject's time series for some node and the average of everyone else's. And then it's doing like every, almost like a cross-validation thing where it's looking at every permutation of that and then taking the average. So you don't always get 1s there. But that's where that 1275 is coming from. It's like an efficient way of storing a symmetric matrix where the diagonal is informative. Okay. Good so far? All right. Is this level of detail helpful? Is this painstaking? Helpful, painstaking? I guess it could be both. Like a sideways thumb. Okay. Okay. Some of you had no comment. You're very kind. But no one. Okay. All right. I'll keep pushing through then. Might as well just finish. Okay. This is like, so when we get to this point, we have our like dynamic connectivity patterns from these 2 groups of people. So that, the code so far, if you want to like apply dynamic connectivity analyses to your data set, the code so far will get you there. Okay. And then the last 2 things we're going to do is visualize the data set, or these patterns. And the key function here is we're going to take the first like n frames of those dynamic connectivity patterns, which like it takes a long time to plot the full thing. So we're just going to plot a subset of them. And then C thresh here is like, when do we draw a connection versus not? So that's like our significance threshold that we're choosing. And that's computed using this formula based on the data. So if you have a preferred way of like multiple comparisons correcting, coming up with a significance threshold, then that could be swapped in for your value of C thresh here. Okay, and then this animate chord uses it's a different plotting library that we actually haven't played around with yet because it doesn't work with collaboratory, but it's called the Hollow Views library, and it produces these kind of neat looking. Well, Hollow Views is actually a wrapper for a different library called Bokeh, which produces these interactive plots. And then you can like, it makes this cool slider here where you can control time by adjusting the slider, and then it gives you the network patterns at different time points. And so this animation is for the intact condition where people listen to the intact story. And then this calls the same code, but for the scrambled or like word scrambled data. So now we're looking at, different time points from the word scrambled data set. And if you wanted, you could say like, okay, well, this is what time point 70 is looking like for the intact condition. What does it look like for the scrambled condition? And then we could like, compare between these. I guess you can't see where I'm pointing to on my screen, but know that I'm pointing to these two plots in a very intuitive way. Okay. Okay. So that's one way of exploring the data. And then that's kind of a fun function to play around with. And then the other way that, the other kind of interesting function here is this animate connectome function. And that takes in node locations and then a set of connectivity patterns and a significance threshold. And then it like chunks through and creates the frames of this movie and then stitches them together into a video. And HTML is a, well, it's like the language that web pages are written in. It's this function embeds stuff in HTML, which can be viewed in these notebooks. And so here we have like a video that is created from this animation, and that's being displayed as an HTML object. So you can like, play the video in the notebook. One weird thing that I could not figure out how to debug, I spent like a long time on it. For some reason, it always prints out the last frame, which I think it's just like not as clean as I would like it to be. I have no idea why that happens. I could get that frame to disappear and then the entire movie disappears, or I could plot that frame and then the movie plots. So I don't know, found that super annoying, but cannot figure it out. And then we call the same animate connectome function for the different conditions data, and then we get another movie. Okay. So one way to think about the like animate chord or plot chord and whatever it's called, animate chord and animate connectome. These are like two examples of other functions that you might want to feed your like dynamic connectivity patterns into. And in this case, we're just visualizing the data. But if you wanted to do some sort of statistical analysis to say like, okay, when are the patterns different across conditions, or feed it into a different model that you think might be interesting, then like you could do that in a similar way. All right. Well, that gets us through the notebook. Any questions there? It's a lot of stuff happening. Okay. Well, there you go. Perhaps you'll use this to apply time series network analyses or time series analyses to your own data set. We'll see. Okay. So I'm going to stop screen sharing. Okay. So that's going to be module 9. That's time series analysis, just like a few minutes of walking through a notebook. Okay. So like this module, many modules in this course really could have been expanded out into their own like term-long courses. So sadly, we have to leave many of these topics like at the survey and introduction states, if that. But if you came across some topics you're especially interested in or that you think might be useful in your research, hopefully, not just for this module, but for others too, hopefully you now have some a few demos and practical examples to help get you going. And then also you have some pointers to other resources if you want to really get deeper into those topics. So perhaps you'll find those useful. I also wanted to tell you, I've been really impressed with how far you've all come this term. So if you remember way back at the start of the course, a decent portion of you had never used Python before, and a few of you had never coded anything before. And now, like, we've gotten through some pretty advanced stuff. So good on you. Like online learning and pandemics are tough, and I'm proud of you for sticking with it and powering through. And it's been a year of this stuff, so you're going strong, and I'm really impressed. The main thing that I hope you'll take away from this term is the sense of like being able to look up how to use new tools and libraries. Like now that you know kind of how to program in Python, that's really where the power of this stuff comes from. So like you want to be able to look up new tools and libraries and then start applying them to your own data from your own research. So you don't, hopefully you now appreciate that you don't need to memorize stuff. You just really need to build up intuitions for how to look stuff up. And then coding is all about just constantly looking stuff up. And then, yeah, I hope you found this course useful. Thanks for taking it. And I'd love to hear from you if you end up using some of these approaches in your own work. Hope you keep in touch. And yeah, thanks so much for a great term. And see you all around. Take care, everyone.
Thank you.
Thank you.
Bye.